Welcome again. Today we will discuss lanthanides in organic synthesis, and today we will discuss samarium and samarium iodide based reagents. So, lanthanides, if you see, this is the 6th row, and after cesium and barium these lanthanides are there. They are total 15 elements and they have similar properties, that is why they are kept in the same position, and this is the 7th row, and here this is the 15 elements also there, and these are called actinides. So, this is lanthanides and these are called actinides. So, the lanthanides are first discovered in 1787 when an unusual black mineral was found in Ytterby, Sweden. This mineral, now known as gadolinite, was later separated into the various lanthanide elements. And 1794 Professor Gadolin obtained yttria, an impure form of yttrium oxide, from the mineral. So, you can see this is the ytterbium is present here. After lanthanum, so lanthanum actually it has 4F0. That is why sometimes it is not called lanthanide, but because its property is similar to other lanthanides, so sometimes it is called the lanthanide. So, here we see the cerium, this is the symbol and this is the electronic configuration 4F1, 5D1, 6S2, and praseodymium, and this is the observed. So, here you can see this is the observed, because accordingly one electron will stay in the 5D, but it is coming to 4F and it is becoming 4F3. So, these all are observed, and the preference for the electron to stay in 4F orbital, except gadolinium, where this is half filled 4F7. So, this is half filled, that is why one electron went to 5D1, and this is lutetium, here also 4F14 5D1, this is full filled. So, now we will see the oxidation states. Most stable oxidation state of the lanthanide is +3, and for dye-positive lanthanides, samarium +2 F6 nearly half filled, europium +2 F7 half filled, and ytterbium +2, that is F14 filled, are known with relative stability in H2, being europium +2 more stable than ytterbium plus, this is much more stable than samarium +2. So, this is half filled. So, half filled is more stable than full filled. So, this is full filled. So, half filled is more stable than full filled, because it will be more stable if there is a one electron in each orbital. And cerium +4 F0, ceric chloride CCl4 we have seen earlier also. So, Ceras 4 plus is the only tetrapositive lanthanide stable in water. Now, we will discuss ionization energy. So, this you can see I1, this black one I1, green is I2, red is I3, this is I4, and you can see this I1 and I2 are almost same for all, means the I1 value for the lanthanides, all lanthanides are same, and similarly the I2 value are same. And ionization energy reflects relative energies of the 4F, 5D, 6S orbitals. 6S electrons are removed first, hence first two ionization energies for all lanthanides are essentially the same. So, it is almost linear, because the electrons are removed from the same 6S orbitals. Now, third ionization energy usually results from removal of an electron from the 5D orbitals, and you can see there is difference. So, it is not linear, and this is more stable, because this gadolinium +3, this is 4f7. So this is half filled. So it is more about the stability of the ion that tells the ionization energy. The stability is more means ionization energy will be less. Fourth, ionization energy reflects successive electron occupation of 4f orbitals. So here you can see the cerium plus 4 is the most stable. So this is the most stable here, and others are very high energy. So cerium plus 4 is most stable, and it is stable also in water. Now properties of lanthanide ions. So there is a sharp decrease in the ionic ready value of +3. So here we have seen the +3, and here +4 also, here +2. So all cases, if you go along the lanthanide series, the ionic ready sharply decrease. So why it is? So ionic ready decreases with increasing atomic number. Now due to ineffective shielding of the 4f electrons, increase effective nuclear charge, because shielding by the 4f electrons are not so good. That is why the effective nuclear charge is very high. Upon ionization, f orbitals are greatly contracted towards the nucleus, effectively eliminates covalent bonding interaction with ligands. Highly ionic ligand metal interaction, no need for orbital overlap. This will also see the properties of lanthanides. Now we will discuss lanthanide comparison to 3D metals. This is the reactivity of the lanthanide elements. They readily tarnish in air, reacting slowly with cold water and rapidly with dilute acid. The reactivity of the elements is greater than that of the transition metals akin to group 2 metal. So they are quite similar to group 2 metals, and their reactivity also sometimes similar to group 2 metals. Coordination number in complexes. In comparison with the 3D metals, lanthanides exhibit a much greater range of coordination numbers in their compound. So this is important, they give much greater range. On grounds of size alone, it would be expected that coordination numbers would be greater for lanthanides than for the 3D metals. But typical values lie between 6 and 12. In contrast, the norm for the 3D metals is between 4 to 6. So here higher coordination number. Also organometallic compounds, in general there are very few or none of the compounds with familiar pi acceptor ligands, as for example carbon monoxide Na+, RnCN2, owing to their unwillingness to form multiple bonds such as Ln double bond O, reflecting the contracted nature of the 4f orbitals and their non-availability to participate in Ln O pi bonds. So 4f orbitals are very buried inside, so they are not available for bonding. That is why this pi acceptor ligand complexes are not there. On the other hand, for a 3D metal, use of the 4s, 4p and 3d orbitals means that 9 orbitals are available for bonding corresponding to 8 electrons. These are supplied by the metal and their associated ligands. And we already seen there are a lot of transition metal carbon monoxide complexes. So they easily form the complexes with pi acceptor ligands. On the other hand, lanthanides do not. Electronic properties. The optical and magnetic properties of lanthanide ions are very different to those of the 3D transition metals. The 4f electrons are well shielded by the 5s2, 5p6 orbitals, so that these electrons are largely uninvolved in bonding. Shielding from ligands means that there is no quenching of the orbital moment, and their spectroscopic and magnetic properties are thus largely uninfluenced by the ligand. Now electronic spectra. Many of the lanthanide 3 ions in solution are so weakly colored as to appear colorless. The 3 principal exceptions being PR3+, ND3+, and ER3+. In comparison with the DD transition in the electron spectra of the complexes of the 3D metals, lanthanide complexes have much weaker FF interaction. So this DD transition is very strong. Transition strong. On the other hand, FF transition is very weak. Magnetic properties: the transition metals have weak spin orbit coupling and strong ligand field splitting. Lanthanides have opposite actually. They have strong spin orbit coupling, but so weak ligand field effect, but transition metals have strong ligand field effect. This was the reviewed encyclopedia of inorganic and inorganic chemistry. Now, we will discuss overview of samarium promoted reaction, cyclopropanation of allylic alcohols, iodomethylation of carbonate compounds, cyclopropanols from alpha halogen substituted ketones or 1,2-dibenzoyl ethanes. This is actually 1,4-diketone, that we will see, and 1-pot synthesis of cyclopropanols from ketones. Also 1-pot synthesis of cyclopropanols from esters, amides and acid chloride. So, samarium, this chemistry is very much rich to generate cyclopropane as well as the cyclopropanol, that we will see. Samarium promoted cyclopropanation of allylic alcohols. First we will discuss the use of samarium mercury amalgam in conjunction with diiodomethane. So, this is this, and this is chloroiodomethane, this is ICH2Cl, to generate samarium carbenoids for the efficient cyclopropanation of allylic alcohols. These hydroxyl directed cyclopropanations occur under mild conditions and allow a wide range of substitution at both the olefin and the carbonyl carbon in allylic alcohol substrates. High yields and high diastereoselectivities are observed for many substrates. So, this also very important, the high diastereoselectivity that has been obtained for the cyclopropanation of allylic alcohols. So, that we will see also. So, this is example. Here you can see secondary alcohol is there. So, this is cyclohexenol. This is allylic alcohol and with samarium mercury. So, this mercury, what is that? Ag increases reactivity of samarium. So, if you do not put mercury, then the reactivity is less. And here samarium amalgam ICH2Cl is there, THA minus 78 degrees centigrade to room temperature, you get 96% yield of this product. And here you can see the cyclopropyl group is the same side of OH group. So, that means this is OH directed cyclopropanation, that we will see in the mechanism later. Here also this is 7-member ring. Here also you get high diastereoselectivity, and under the same condition here diiodomethane is used, minus 78 degrees centigrade to room temperature, THA solvent. However, the yield is little less, 64%, but the diastereoselectivity is still high, greater than 30:1. So, this is the major diastereomer. Here also the cyclopropyl group is in the same site of the hydroxy group, and this is 8-member ring. With same conditions, samarium amalgam CH2I2 THA minus 78 degrees centigrade to room temperature. Here you get good yield of 85%, and here the diastereoselectivity also is very high, greater than 40:1. So, this means the secondary allylic alcohols can give high diastereoselectivity for the cyclopropanation with samarium amalgam and CH2I2 or ICH2Cl. So, this is very important, and with chiral secondary alcohols like this one, you put samarium CH2I2, you get 99% yield of this product, and you can see the diastereoselectivity is greater than 200:1. So, this hydroxy and cyclopropyl is in the same side. If you put now cis1, So, this is trans olefin, cis olefin. Cis olefin also with CH2I2 samarium you get high yield 99%, and here also the diastereomeric ratio is very high. The cyclopropyl group is the same side of hydroxy group. And this one we have already seen cyclohexenol, and here with samarium CH3 CHI2 you get 5:1 diastereomeric ratio XO:2 On the other hand, if you put diethyl zinc CH3 CHI2, the diastereomeric ratio is 1.6:1. So, this is the best option if you want the diastereoselective cyclopropanation of allylic alcohol, then this samarium CH2I2 or CH3 CHI2 is the best option. Now, we will see the mechanism. So, here you can see R dash is there, R double dash, R triple dash, there is another R is present, and this is the chiral center. So, chiral center, and with samarium amalgam CH2X2 THA minus 78 degree centigrade, you get two diastereomer AB. Here this has been drawn in the plane. So, there can be two diastereomer, either this is that side or it is other side, because this is in the plane, then you can draw the other diastereomer like this. So, there are two diastereomers. And this diastereoselectivity can be explained by these transition states. In substrate, diastereoselectivity in substrates from this series in which both R and R double dash are relatively small alkyl groups. When R is equal to methyl, essentially no selectivity was observed and the product ratio H to B remains close to unity. So, earlier we have seen earlier slide, if there is a tertiary butyl group, then if you have a methyl group you can get, otherwise the diastereoselectivity is very low when R is equal to, that can be explained because R is here you can see, and here R is here. So, here R is in the steric repulsion in the other transition state, but here it is antiperiplanar. So, here it is antiperiplanar. So, the size of R is important for the energy difference between these two transition states A dash and B dash. However, as R was increased in size from methyl to isopropyl and tertiary butyl product mixtures with quite high ratio of diastereomers greater than 200:1 of A is to be often isolated. So, this is important. If R is becoming tertiary butyl, then you can get high diastereomeric ratio, because then the steric repulsion here will be more. So, this is R dash and this is R double dash and this is R triple dash, here R is there. And if you see carefully, we are looking at this carbon-carbon bond. So, this carbon-carbon bond we are looking, and then we have drawn this Newman projection, and here also you can see this OH has been binding with samarium, also CH2I2, that CH2 is connected with samarium as well as this I, and now this carbenoid, that is the making the cyclopropanation, so reacting with this double bond. For substrates in which R represents a small alkyl group in disubstituted E-allylic alcohols, R dash is equal to hydrogen, there is apparently a small energy difference between the conformations represented as A dash and B dash. Now, advantage of using samarium promoted cyclopropanation reaction, that here you can see two double bond and present. Of course, one is allylic alcohol, this is allylic alcohol and this is simple olefin, and this compound is called geraniol. And now, if you put reagent, you can get, this is down hydrogen, three kinds of product. One is a cyclopropanation here, that is A. Another is cyclopropanation is both double bond, then it is called B compound, and if it is here in the olefin, not in the allylic alcohol, that is also another possibility. So, 3 compounds can be formed. So, this is actually regioisomers. Now, if you put diethyl zinc CH2I2, then A is formed 74%, A, that is the major, but you get some amount of B and C, 3%, 2%. On the other hand, if triisobutyl aluminium with CH2I2, so this is aluminium, you get only 1% A, 4% B and 76% C. So, this becomes major here with triisobutyl aluminium. So, this is interesting. And now, samarium mercury ICH2Cl, whatever we are studying today, there you get 98% of this one. So, this is 98% and these two are 0. So, this means highly selective. So, with samarium mercury ICH2Cl, you get regioselective as well as the stereoselective cyclopropanation. So, the high regioisomer as well as the diastereoselectivity obtained. Here this stereochemistry is retained, here they are cis, here also cis. And this is the Journal of Organic Chemistry 1989. Now, we will discuss another reaction, that is iodomethylation of carbonyl compound. So, with the same reagent we will see what happens with carbonyl compound. Now, if you have a carbonyl compound R1COR2 with CH2I2 samarium THF 0 to 25 degree centigrade, you get this compound. So, what happens? The CH2I group added and as a nucleophile. So, CH2I is nucleophile and it added to the carbonyl compound. So, this is simply addition reaction, and that is called iodomethylation also, because iodomethyl group has come, that is why it is called iodomethylation of carbonyl compound. Now, molar ratio will be 1:3:2, ketone will be 1, 3 will be CH2I2 and 2 will be samarium. And then if you treat this adamantyl ketone, so this is adamantyl ketone or adamantone, and then with CH2I2 samarium you get this. This is a quaternary center and carbonyl become OH-CH2I. Similarly with cyclohexenone also, if you put CH2I2 samarium, here the cyclopropanation did not happen. Cyclopropanation did not happen because we have already seen that only allylic alcohol react. So, simple olefin will not do the cyclopropanation. Instead, it will give reaction with the carbonyl part and you get this hydroxy CH2I group. Also, aldehyde can be reacted with this reagent CH2I to samarium and you get this secondary alcohol. And in this case with ketone you get tertiary alcohol. Now, we will see cyclopropanols from alpha halogen substituted ketones or 1,2-benzoyl ethane. So, if you have a alpha bromo or alpha halo substitution of the ketone, then you get defined product. Alpha halogen ketones are treated with diiodomethane and samarium in THF at 0 degree centigrade, 1:3:3 halogen ketone CH2I to samarium to give cyclopropanols as the major products. It is noteworthy that chloro as well as iodo and bromo ketones reacted smoothly to afford the corresponding cyclopropanols. You can see this is the alpha halo ketone. So, with alpha halo ketone you get cyclopropanol. So, here that means or the halo reacted first and then you get enolate and then only this possible. We will see the mechanism details. So, here you can see R1 is equal to pH, R2 is equal to H, X is equal to Cl, you get 37%, and if it is bromide then you get 81%, and if it is iodide then you get 88%. So, yield increase. So, iodides are the better. So, that means the halo group is important, and here the other groups are there 67%, X is equal to chlorine 49, X is equal to Br 55, if R2 is equal to methyl, and this is cyclic ketone also 81% yield you can get. Similar conditions, alpha bromoketones 3 and 4 were converted into bis cyclopropanols 5 and 6 in 62% and 29% yields respectively. Bis alpha bromoketone. Like here PHCO, CHBr, CH2 and CHBr, COPH. Here with CH2I2 samarium, of course more equivalent you have to it. And if n is equal to 1, then it is 5, that case you get 62% yield. So, this will give 62%, and n is equal to 3, then you get 29%. So, this means this reaction is quite general for alpha bromoketones. So, the cyclopropanations proceed through the pathway illustrated. The alpha halogenoKetones and 1,4-diketones are reduced by samarium iodide or metallic samarium to generate samarium enolate 7. So, this is the samarium enolate, this is important, which in turn undergo a Siemens-Smith type cyclopropanation with samarium carbonate species to afford the product. So, alpha halogenoKetone or aromatic 1,4-diketone, that also we will see. When you treat with samarium and CH2I2, then you get this enolate, or you simply if you start with samarium iodide here, this enolate will form. So, enolate. So, what is happening here? That means when you put samarium, then samarium inserts this CX bond. So, here you get samarium, and now this will be enolate, and when enolate, the samarium will go with the enolate. So, it will be like this, that is what is happening here. And after that, if you put ICH2SMI2 or ICH2SMI, so this will give the cyclopropanation, that is this. And after hydrolysis, so this is water, then you get the cyclopropanol. So, this is very important, that means this enolate is very important, and enolate after cyclopropanation you giving the cyclopropyl samarium species, and then after hydrolysis you give the cyclopropanols. Cyclopropanols are produced from 1,4-diketones having aromatic groups. This is also special. So, this is 1,4-aromatic diketone, and here if you see this product, that means this bond has been broken. So, samarium has been able to break this bond and making this enolate, and after that enolate formation with CH2I2 samarium you get the cyclopropanation, and you are getting this 1-phenyl cyclopropanol in 66% yield. So, this is very important, either alpha halogenoKetone or 1,4-diketone aromatic can give this kind of product. And one-part synthesis of cyclopropanols from ketones also is possible. So, here you do not need or alpha haloketone, because we have seen that halogen is there only to make an enolate, and now if you have external base, if the enolate can be formed from the ketone, and then if you put this second step samarium CH2I2 THF 0 degree centigrade, whether you can get this product or not. In fact, this is GS, and if you put LDA, this is very strong base, so strong base LDA, and then you can get this enolate, and this enolate then reacting with CH2I2 samarium, first this one, samarium takes this, and after that the cyclopropanation will happen. Cyclopropanation of the double bond will give this cyclopropanol after hydrolysis. So, this is cyclopropanols. And the defined ketones can be made enolates, like here cyclohexanone. Cyclohexanone, if you treat with first LDA, LDA will make the enolate and then react with CH2I2 samarium, THF 0 degree centigrade, then you get this product. So, these come from the CH2 group here. So, this is the enolate chemistry, enolate chemistry, and that enolate is reacting with the carbenoid to generate the cyclopropanol in 56% yield. Also, if you have a acetophenone, this is acetophenone, and acetophenone with LDA also make the enolate, and after that CH2I2 samarium you get this cyclopropanol in 60% yield. Now, we will discuss two kinds of enolates can be formed. We know one is kinetic enolate, another is thermodynamic enolate, and depending on the reaction condition we can get two different kind of products. Like 2-methyl cyclohexanone, if you treat with LDA minus 70 degree centigrade and then you put CH2I2 samarium, you get the kinetically stable product. In fact, before that with LDA minus 78 degree centigrade, you get the kinetically stable enolate or kinetic enolate. And kinetic enolate will be this side, because this side is substituted, and after that you get this product. On the other hand, at room temperature, because you allowed the reaction to equilibrate, and after that only thermodynamically stable enolate will form. So, this will give thermodynamically stable enolate, and after that with CH2I2 samarium you get this. So, one case the enolate from this side, another case enolate from this side, that is why this side is the cyclopropanol happen. Also, if you put unsymmetrical ketone like this, one side methyl, another side butyl, and with pH 3 CLI, this is a bulky base also, and then you put this CH2I2 samarium, you get this. So, what does it means? The terminal carbon has reacted, that is the less substituted carbon has reacted. So, here you can see this is methyl and this is butyl. So, with strong base, bulky base, here you get this one enolate formation, because this is the kinetic enolate, and after CH2I2 samarium you get this, and after hydrolysis, and of course the samarium is there, CH2I2, the cyclopropanation will happen, and after hydrolysis, so water will be later, then you get this cyclopropanol. Also, one-part synthesis of cyclopropanols from esters, amides and acid chloride is possible. So, we have seen that is the enolate chemistry. So, enolate chemistry we have seen for the alpha bromoketone and as well as the ketone with base, and now if you put esters or amides, acid chloride, that case also you get these cyclopropanols. So, what is happening here, that if you have a leaving group X is equal to OR Cl NR2, that is the tertiary amide, and then if you put CH2I2 samarium, then a nucleophilic substitution reaction happens. So, this is nucleophilic substitution at carbonyl, because this is a living group and the CH2I we have already seen that come here and you get this, and this is in fact now alpha iodo-ketone. So, we know that alpha haloketone will generate the enolate with samarium or samarium I2, that is what has been done here. This is the enolate. So, this is samarium enolate, and after that the cyclopropanation will happen, CH2I to samarium, and after hydrolysis you get the cyclopropanol. So, this is very important, that when you have a ester acid chloride tertiary amide, then this substitution reaction at the carbonyl carbon is happening and you get this alpha iodo-ketone, and after that enolate is forming, and then the remaining steps are similar. Now, we will discuss samarium iodide. So, samarium iodide is an useful reagent in organic synthesis and many transformations has been carried out with samarium iodide. So, samarium iodide is an inorganic compound with the formula SmI2. When employed as a solution for organic synthesis, it is known as Kagan's reagent, and samarium I2 is green solid and its solutions are green as well. It is a strong one electron reducing agent that is used in organic synthesis, and this is a general reaction with halides, and AIBN and tributyl tin hydride also can generate a radical, that is common, and here we will see the samarium iodide can do the similar radical generation. It is ionic, so R gets plus X minus, and that R plus is reduced by samarium to generate the radical. So, one electron goes to R plus, then it becomes radical, and this radical can be quenched with samarium iodide to get this R minus samarium 3, then after proton source you get RH. So, RAX can be converted to RH, also R-DOS can go to RH also radical, and this is the dimerization. So, radical forms, then it can carry out many kind of reaction, that also we will see later, that R-DOS can be used for different carbon-carbon as well as carbon heteroatom bond formations. So, first we will discuss preparation of samarium iodide. First procedure 1, this is Kagan's method using 1,2-diiodoethane. So, this is the 1,2-diiodoethane, and this is interesting, here you get the ethylene gas. So, this gas will be out, so the reaction will go to the forward direction. Forward direction you get the reaction, it will be quite fast. 3 equivalent of samarium metal, and then 3 equivalent this, we will give 2 equivalent of samarium I3, 3 equivalent of ethylene and samarium. This samarium I3 and samarium again will react to generate the samarium I2. Inamoto method, here he used iodine actually. So, samarium plus 3 I2, 2 SM I3 plus samarium. Similarly, the second step is same, 2 SM I3 plus SAM, SM is 3 SM I2. So, this is actually same 3 SM I2 is formed here. Now, we will see that use of additives and co-solvents also important in samarium iodide reactions. One of the most fascinating feature of samarium iodide is the ability to modify its behavior through the use of co-solvents or additives. So, this is very important. It can be more reactive if you put sometimes co-solvents like HMPA and also water. For example, co-solvents or additives can be used to control the rate of reduction or the chemo or stereoselectivity of reactions. Additives commonly utilized to fine tune the reactivity of samarium iodide. It can be classified into 3 major groups. One is the Lewis base, these are actually co-solvents, Lewis basic co-solvent like HMPA and other electron donor ligands, chelating ethers, also water. Proton source, here it is predominantly alcohol and water, and inorganic additives, nickel iodide, ferric chloride, etc. So, proton source we will first discuss. Many reactions mediated by samarium iodide requires the presence of a proton donor. The primary role of the proton donor is to quench alkoxide and carbon ions produced as intermediates upon reduction or reductive coupling. This we have seen in the halide reaction with samarium iodide, that you need a proton source to quench the alkoxide or carbon ion. The most commonly utilized proton donors are alcohols, glycols and water. It is now very clear, however, that proton donors can have a considerable impact on the efficiency of samarium iodide mediated reactions and their regiochemical and stereochemical outcome. So, that means there is a more effect of this proton source. Sometimes they are actually increases the reactivity of the samarium. Inorganic additives, inorganic salts are another important additive used to enhance the rate and selectivity of samarium iodide mediated reactions. And this is basic co-solvents. So, Lewis basic co-solvents. Basic co-solvents dissociate samarium iodide aggregates in THF. This is very important. The aggregates has been dissociated by basic co-solvents. Also, basic co-solvents may perturb the electron donating orbital of samarium 2 and raise its energy, thus increasing the samarium to samarium 3 reduction potential. So, this is very important, increases reduction potential. So, that means the reaction will be much faster. Reduction potential samarium to samarium 3. Overview of samarium iodide promoted reactions. So, today we will discuss the reduction of alkyl halides with samarium iodide, beta elimination reactions by samarium iodide, reduction of alkyl halides, the reduction of ketones and aldehydes with samarium iodide, the reduction of carboxylic acid esters and amides with samarium iodide. So, the reduction of alkyl halides with samarium iodide is a popular reaction, that is called the dehalogenation reaction, like tributyl tenhalide and AIBN does. So, here samarium iodide reduces alkyl halides with the ease of reduction following the expected order. Iodides more than bromides, that is more than chlorides. Examples we will see, like here N-decyl bromide with samarium iodide only, THF 48 hours, 95% yield of this product in decane you get from this bromide. So, this is actually dehalogenation. Also, with chloride the reaction does not occur. With samarium iodide THF under same condition, the reaction does not happen. That means the carbon shell bond is strong. By adding of additives, you can also put additive like HMPA, hexamethyl phosphorylamide, and with this one the reactivity is increased, and only 10 minutes, earlier it took 48 hours, now only 10 minutes you get this product in decane in greater than 95%. And now chloride also can be used with samarium iodide, HMPA, THF 60 degree centigrade, 95% yield of the N decane. So, that means tuning the reactivity. Actually, it is increasing the reactivity, tuning the reactivity with HMPA. So, this is very important. With HMPA, samarium iodide become more stronger reducing agent. Some more examples, here aryl bromide is there, and samarium iodide, THF, HMPA, room temperature, you get this. And so, this is very important in samarium iodide mediated reaction. If there are different groups, so the highly reactive bond will first react. So, here ester is untouched. But we will see later that ester can be also reduced with samarium iodide. And here a double bond is present, and this is many chiral centers are present. Only selectively with samarium iodide, THF, HMPA, isopropanol, 99% yield. So when chloride is there, for chlorides HMPA is must, otherwise no reaction. And isopropanol is the proton source, then you get 99% yield of this product. And this is vinyl bromide. With vinyl bromide also you can get the reaction. Here also you need the HMPA, samarium iodide 2.5 equivalent, THF HMPA, room temperature 20 minutes, you get this styrene in 95% yield. Now we will see the reduction of ketones and aldehydes with samarium iodide. So if you don't put LDA, then they will be reduced actually. So samarium iodide reduces aldehydes and ketones to the corresponding alcohols, as there are numerous hydride reducing agent for the reduction of aldehydes and ketones. This functional group transformation has not been used widely. However, in certain cases it has been used to get the diastereoselective product, like here a ketone is present and ester is present. So selectively the ketone has to be reduced also. If you need the one stereoisomer, then this condition samarium iodide, THF, water. So in this case water may be less equivalent, maybe 1-2 equivalent, because if you give more, then this ester will reduce. Water also is important for the reduction of esters. And room temperature 5 minutes, 90% yield, you get this one. So here this OTB DMS group is untouched, this ester is untouched, and selectively the hydride comes from the down phase, so that you get the beta alcohol. So what is the mechanism for this ketone reduction? So of course the single electron transfer will happen to the aldehyde or ketone, generates a ketyl radical anion 3 that can form a dimeric or polymeric ion pairs 4. So like this, the radical anion, this is actually radical anion, and this radical anion will stay as a dimer. 2 atom of metal is present here, and in the presence of proton source, the OM bond of the metal ketyl radical anion is protonated to form a carbonyl radical 5. So after protonation you get this, because OM is replaced by OH now, carbonyl radical. And further reduction then forms a hydroxyalkyl carbanion 6. Again another electron comes, then like Barch reduction we have seen, hydroxyalkyl carbon 6 and protonation give an alcohol product. So this is alcohol. So like Barch reduction we have seen there the benzene system reduced, here the ketone is reducing, and in the similar mechanism, the radical, then the proton, and then radical, then again the anion is forming. Competing processes including dimerization of the metal ketyl radical anion to give pinnacle products, or disproportionation to give an enolate and alkoxide. So that is also possible. We will see later the competing pathways, that is the pinnacle formation. So this is pinnacle, because this radical it can dimerize easily. Also it can generate enolates and alkoxide by disproportionation. So that is also possible from this dimer, that one goes to the enolate, another goes to the alkoxide. Now we will see the generality and the scope of this carbonyl reduction with samarium iodide. This is beta hydroxyketone. Now whether we know that the hydroxy group is important, hydroxy group binds with samarium, that we have seen in the cyclopropanation reaction, samarium CH2I2. Here we will see the samarium iodide mediated reduction at 0 degree centigrade. Here also this hydroxy group binding, because you get a diastereomeric product greater than 99:1. That means the hydroxy group is binding, and then the stereoselective. So this means the stereoselective reduction is happening here. So what could be the mechanism of this? So samarium I2 first reacts with OH and then it is making reduction, then the ketyl radical is forming, and now the samarium 3 will coordinate with OH as well as this oxygen, and now it will take chair conformation of the anion. So, after one electron reduction you get the anion, and this anion means there samarium will come. Then cyclohexyl will be like this, and samarium 3 will take an equatorial position. Samarium 3 equatorial position. And methyl is here, and this oxygen and the OH is coordinating with another molecule of samarium. And here you can see this cyclohexyl and methyl are in the opposite side, and here we will give first this alcohol, of course, this OH cyclohexyl. And then if you draw a zigzag, because and then here this OH are in the same side, but after you make this methyl here, then they will be trans. So, this is trans. The reaction proceeds by initial coordination of samarium 2 to the free hydroxyl, followed by intramolecular electron transfer to the ketone carbonate to form ketyl radical anion. So, this is the ketyl radical anion. A second electron transfer gives alkyl samarium, in which C-samarium bond adopts a pseudo-equatorial position due to the steric demand of samarium and its associated ligands before being protonated by methanol to give the product. So, this is very important, the chair conformation. Now, if you have a amine, so this is beta aminoketone, then if it is a PMP group, so PMP is paramethoxyphenyl, so this is the PMP. So, NH-PMP, that means here NH is there. Then you get the, so similar like hydroxyketone, you get the trans, and major diastereomer is higher than 99:1. So, under the similar conditions, samarium iodide THA methanol 0 degree centigrade, you get 98% yield of this product. So, here also we can think that similar like earlier we have seen that for the hydroxyketone, here also this NH-PMP that will coordinate with the samarium. Here methyl, this coordination will happen with NH-PMP. That is why you get this similar selectivity greater than 99:1. On the other hand, if R is equal to acetyl, and interestingly they are now seen, so seen is measured here, and you get 96% yield under same condition, and the diastereomeric ratio is almost 9:1. So, what is happening here? So, this is cyclohexyl, and what happens here? 8-member ring is formed because this NCO, this amide carbonyl bond, that is coordinated with samarium 3, and also this somehow this samarium takes a pseudo axial position because of this coordination, and methyl stays here. So, that is why you get a defined geometry here. So, this is an 8-member ring. So, it is quite flexible because of this coordination, maybe this also coordination is samarium 3, because this is very much nucleophilic, this wants to coordinate with samarium, and then this to samarium wants to stay close by or close to the amide carbonyl, and that is why you get this geometry. Also hydroxy directed, so this is hydroxy directed, we have already seen one, beta hydroxyketone. So, here You can see this is the trans is forming here, that is obtained also 96:4 under salmon iodide 3 equivalent methanol THA minus 78 degrees centigrade, 96% yield. Now we will see fragmentation reactions triggered by carbonyl reduction with salmon iodide. Like here, if you have a ketone with a cyclopropyl group, alpha beta position, then this cyclopropyl group can be cleaved, because we know this is the radical chemistry here happening, like salmon iodide HMPA methanol, it will give this radical anion, and this radical then will cleave this cyclopropyl group and you get this. So, enol will form, you can see here this radical going here, and after quenching again of course samarium will come, samarium iodide, and then the methanol, then you get this enol. So, this methyl is coming from the cyclopropyl group. So, this is very important. If your ketone has a cyclopropyl group, then there is a chance to break this cyclopropyl group. Also here this samarium iodide THF DMPU minus 78 degrees centigrade to room temperature, you get 79% yield of this product. So, similarly here this radical anion will make the enolate, and here this radical will form, and that radical will react again with this triple bond, because nicely it is fitted, because 5 exo dig will happen and you get exocyclic olefin here. Now we will see, so far we have seen that carbonyl group like ketone can be reduced in presence of ester. Now we will see that under which condition the reduction of carboxylic acid, esters and amides with samarium iodide is possible. So, generally samarium iodide not reduce carboxylic acid, esters, amides, but by adding some additives it will reduce it, and generally water you have to add maybe 4 equivalent of water, that we will see. Like here benzoic acid, also base is added here, samarium iodide 4 equivalent, sodium hydroxide 8 equivalent, H2O THF, solvent mixture, room temperature 1 minute. So, this is very fast reaction, you get 91% yield of this benzyl alcohol. Here base is not added. So, if you have a R is equal to OH, that is the carboxylic acid, only methyl group is present, and R is equal to NH2, so this is carboxylic acid, and this is amide. We will see some more example. So, with cinnamic acid, this is very important. If you have a alpha beta unsaturated acid like cinnamic acid with samarium iodide 4 equivalent water, also if you add, a double bond only is reduced. So, double bond reduction is very fast, because double bond is conjugated with this electron withdrawing group, and you get this hydrocinamic acid in 99% yield. Also benzoic acid derivative, we have already seen the benzyl alcohol will form, like here orthochloro also. Sometimes chlorine group can be eliminated, like here you get this is the major chlorine, because we know the samarium iodide can also react the aryl chloride under strong condition, because water is added, reactivity increase. So, you can get the dechlorination also. Here meta case also you do not get this. So, here dehalogenation is slow. Ortho case, because ortho is close to the electron withdrawing group, but meta case it is quite far, so it does not happen. Also para cases also you can see this slow, the dehalogenation is slow, but you get some product actually, 15% you get. So, meta case is best, dehalogenation is slowest here actually. Now, we will see the esters. Here also like acid, the double bond reduction is fast. So, here this methyl hydrocinamate is formed in 99% yield, and the ester group did not reduce here. Here this methyl ester goes to alcohol with orthochloro, similarly here 53% this dehalogenation, 23% this. With parachloro, this is major, 89% you get this with parachloro. So, dehalogenation is slow, Dehalogenation is slow. And this is very important, a nitro and CO2 Me group is there. So, with samarium iodide selectively the A star is reduced. So, A star is reduced compared to nitro. So, nitro is untouched here, you get 89% of this product. And without water, this is mild reducing agent. So, mild reducing agent. And Kagan already shown earlier also that cinnamic acid can be reduce the double bond. So, these are the EWG. So, olefin is connected with EWG, then the double bond can be reduced like A star also. Just samarium iodide 2 equivalent methanol, you can get this. So, without EWG. Without EWG, that is the cinnamyl alcohol, the no reaction of the double bond. So, double bond which is conjugated with electron withdrawing group, then only the reduction will happen. Like cinnamyl alcohol, the reaction did not happen. Also, with cinnamaldehyde, you get polymers because here the both is competitive, the double bond as well as the aldehyde group, that is why you get polymers. And with cyclohexanone, you can get the ketone reduction is first also here, 67% yield of this one, and double bond reduction you get 28% yield. So, ketone reduction, ketone is first, ketone aldehyde is first compared to double bond. So, today in the reaction we have first discussed samarium mediated cyclopropanation reaction. We have seen samarium CH2I2 and we have seen defined allylic alcohols can be done cyclopropanation in highly diastereoselective as well as regioselective manner. So, if you have other olefin, then that olefin does not react, only allylic olefin. Then we have seen this cyclopropanol chemistry. First we have seen the alpha bromoketone because it is going by the enolate, samarium enolate is forming, and then the carbenoid is reacting with this double bond and you get the cyclopropanol. Then we have seen that the enolate, if we can form the enolate from the ketone, then also this cyclopropanol formation is happening, and we have seen that you can generate thermodynamic or kinetic enolate. Kinetic enolate at low temperature you have to generate, and then you can get the kinetically stable cyclopropanol. On the other hand, at higher temperature like room temperature you can get the thermodynamic enolate and you can get the thermodynamically stable cyclopropanol. Then we have seen that the esters, tertiary amides and acid chloride when reacting with this samarium CH2I2, then also the cyclopropanol formation is happening. So, there also the alpha iodoketone is forming, and that is generating the enolate and reacting with extra samarium CH2I2 to generate the cyclopropanol. Also, we have seen if you have a aromatic 1,4 ketone, then the cleavage happens, the CC bond, and you generate the enolate again and you get the cyclopropanol. Then we have seen the samarium iodide chemistry, and samarium iodide we have seen that this is very useful for dehalogenation reaction because it is one electron reduction, and defined halides, aromatic halides, also vinyl halides can be dehalogenated and you can get the corresponding alkane in high yield. Then we have seen the ketone reduction. So, ketone reduction is very important. Here the ketyl radical is forming and then the ketyl anion, and here we have seen the hydroxy directed, that is very important. If you have a beta hydroxy ketone, then we have seen the trans product is forming, and also beta amino ketone with NH-PMP, that also gives trans. On the other hand, NHAC gives the syn product. Then we have seen the reductions of esters, amides, and here we have seen that esters, amides can be reduced if you have water in the mixture, and we have seen that this esters defined acid can be reduced to the alcohols. Also we have seen if the cinnamic acid, cinnamic esters is there, then the double bond reduction is much faster process than the reduction. So, only selectively the double bond is reduced. Also we have seen if you do not add the water, then the reaction is very mild, then case also the double bond can be reduced if it is connected with electron withdrawing group. Like cinnamyl alcohol, the double bond is not reduced. Thank you.